Now what happens here is, with momentum in a crash, momentum is always conserved. In other words, we cannot destroy it, create it. It gets transferred, okay, from one object to another, okay, or it can stay in that object. So when you have a crash, the total value of a momentum before, so including all the objects in the system, will have the same total momentum after the collision when you include all the same objects. So for example, the two cars collide here, so one crashing this way, one crashing this way. The system in this case is just these two cars. So if I add the momentum of this car plus the momentum of that one, and being aware that it's probably negative because it's going left, then this total of those two added together is constant. However, if we look at a car that crashes into a wall, well, the car might have a momentum before of, let's say, 10, but when it crashes into the wall, it might have a momentum of 0. So the car has a change of momentum. But we would think that the wall normally doesn't have a change of momentum. So we have, in total, got a change of momentum, and that can't work if momentum is conserved, because the momentum before must be the same as after. So what actually does happen? Well, the Earth continues with a momentum P of 10. Okay? In fact, not actually just the wall, but the wall and car together will continue with a momentum of 10. If you had a rocket flying up in the air and it was initially at rest, if it was at rest, the momentum in total will be 0. So when they're at rest, it'll be 0. Then when the rocket flies into the air, it might gain a momentum of 10. But where did that momentum come from? It can't come from nowhere. We need to conserve it. So that means the momentum of the Earth going the other way must also be equal to 10, and in fact negative 10. So then total will be 0 again. So the 0 we had before must be the same afterwards of 0. So here we might do a couple of examples. So calculate the final velocity of a car B if the car A travels left at 9 meters per second after the collision. So what's the total momentum before? Okay, total momentum before is equal to the momentum of red plus the momentum of, what colour is that? Let's say bronze. Okay, beforehand. So that's going to be 1300 is the mass of red times its velocity, plus negative 20 is the velocity of bronze times 1380. That gives us a total momentum beforehand of negative 8,100 NS. Okay, so that's our total momentum before. So afterwards must also be that. So I'll change colour pens now, and we'll look at after. So afterwards, our total momentum total after is actually going to be equal to negative 8,100. So that means the mass times velocity afterwards must also be the same. So looking at the two values, so car A is travelling left at 9, okay, so that would be minus 9 times 1300. And then we're going to add on the other one, which will be the mass of the bronze, 1380, times its velocity, which we don't know. And that must all equal negative 8,100. So we get something like 3,600 is the total momentum of the red car going left. And we're going to add something to that to get 8,100. Oh, sorry. What am I doing? Sorry, I said the wrong thing there. So this is actually, when we do 9 times 1,300, it gives us a value of 11,000. 700, okay, and then you, must be more than that, then you go take that to the other side, and you effectively add it on, so we're negative 8,100 plus that 11,000 odd, and you get 3,600. Now plus, and that's then going to be equal to 1360 times V. So what does V come out to? So V becomes, running out of room here, 2.7 meters per second. Now, is the total kinetic energy the same after collision as it was before? Okay, so if we work this all out, total kinetic energy, so of the red one before will be half times 1300 times 15 squared. We're going to add that then to the bronze one, so it'll be half times 1380 times 20 squared. And then the kinetic energy afterwards, you do the same thing, so it's going to be 9 half times, let's rub that out, hang on. It'll be half times 1300 times 9 squared plus half times 1380 times 2.7 squared. And you'll find that they're not equal. Okay, so what happens, there's actually a change in energy. So the energy will be dissipated in this collision as heat or something similar. And then what we call this is actually inelastic. So in this case here, we work out what's the change of momentum of this 150 gram bouncing ball. Okay, so it's going down at 8 meters per second, hits the ground, and then bounces back up at 5. So what is it going to be? So change of momentum equals final. So P final minus P initial. So final is going to be negative 5 times 0.15. And we're going to take off then the initial, which will be 8 times 0.15. And that will give us negative 1.95 ns. There's your change of momentum. Now, is the momentum conserved? Well, we've got a change of momentum, so that implies that we have somehow not conserved our momentum because there's been a change. But what would actually happen is there's a change of momentum of the ball going this way of 1.95, and that actually means that there must be a change of momentum of the Earth going the other way of 1.95. Now explosions are very similar to what we've just done before, but the important thing with explosions is that we start from 0, and that means afterwards the total momentum must also be 0. So here you got a bomb, total momentum at that stage is 0, and then afterwards it will still be 0, so once you add up all these vectors of this exploding thing, they will all cancel out to make 0. And here's some more examples of collisions before and after that you can see, but these are essentially explosions. All of them are starting at 0 before, so total momentum equals 0, and that also means afterwards they must also be 0. So all of these, when you do momentum plus the momentum, they must be equal to 0. And because the important thing to remember is there's a negative. So we're going to do here, calculate the velocity of A if B is velocity of 30 after the explosion. So before, so momentum before equals 0. So that means afterwards must also be equal to 0. So 10 times velocity A plus 30 times velocity B actually, which in this case is 30. Okay, must be essentially equal to 0. So we're going to get negative 900 is equal to 10 VA. So in other words, we divide that by 10, we get VA. Okay, so VA equals 90 meters per second, and don't forget the negative.